Alright, let's have a look at question 4. Students travelling on a skateboard along a bumpy road. The word bumpy there gives you a little hint that there will be frictional forces at play. He's holding his school bag, which has a mass of 4 kilograms, and the student and the skateboard have a combined mass of 56. Alright, first question, 4.1, state Newton's law. And Newton's first law. This is one of those that you just need to learn off by heart. An object will remain at rest or continue at uniform velocity unless acted on by an external unbalanced force. 4.2, explain how Newton's first law can be used to explain why the student will slow down and eventually stop as he travels along the bumpy road. You can imagine that happening if you're traveling on your bicycle or any kind of object where you have wheels rolling on the road. If it's bumpy, even if it's not for that matter, frictional forces will slow you down. So how do we use Newton's first law to explain? Well, the bumpy road creates frictional forces, we've mentioned that, which exert an external unbalanced force. And that was the key from Newton's first law, and that force slows down the student. Right, 4.3. To speed up, the student throws his bag behind him. Use a suitable law of motion to explain why this is effective. State the name of the law and explain its application. There are two possibilities here. The first we could use is Newton's third law, and the explanation would be that the student exerts a force on the bag as he throws it, and the bag then, according to Newton's third law, exerts an equal but opposite force back on the student. And it's this equal but opposite force that then accelerates the student. So that's one option. The second option could be to use the law of conservation of momentum. And there we would say that to conserve momentum, the increase in momentum that's caused by, the increase in momentum of the bag caused by throwing it behind him must be balanced by an increase in momentum of the student himself. And because his mass isn't changing, if there's an increase in momentum, then his velocity must increase. 4.4 is a conservation of momentum problem. So we start by stating the law of conservation of momentum. The sum of the momentum before is equal to sum of momentum after. And just indicate your direction. We're taking the original direction as being positive. So we're just making our sign convention explicit. Alright, let's expand that formula. Sum of momentum before. Well, we've got the mass of the student, that's m subscript s. And then added to that the mass of the bag. So that's the total mass of the system times by vi, the initial velocity. And then after he's thrown the bag, the two bodies separate now. So we've got the mass of the student times the final velocity of the student plus the mass of the bag times by the final velocity of the bag. Right, let's look on the left. The mass of the students and the skateboard is given as 56. The mass of the bag is 4. So we add those two together, and the initial velocity is 1.2, and it's in the positive direction. The mass of the student remains at 56. The final velocity of the student is what we're looking for. Mass of the bag is 4. And then he's thrown the bag at a velocity of 0.8 meters per second. Notice it's in the opposite direction, and so it gets the negative sign. And if we solve for the final velocity of the student, we get a value of 1.34 meters per second. But notice that the question asks for an increase in speed, not the final velocity, and so we need to do one further calculation. The increase in velocity is final, 1.34 minus initial 1.2, and it gives us 0.14 meters per second.